Black Beauty, was found on Earth in 2011. Now, scientists say it has revealed a new clue to life on Mars. A mineral trapped within a Martian meteorite that fell to Earth has revealed traces of water on Mars that date back 4.45 billion years, according to new research. The zircon grain may contain the oldest direct evidence of ancient hot water on the red planet, which may have provided environments such as hot springs that are associated with life on Earth. The discovery opens up new ways of understanding whether Mars was ever habitable in its ancient past. It also adds more support to observations already gathered by the fleet of spacecraft orbiting and roaming the red planet, which have spotted evidence of where rivers and lakes once existed on the Martian surface. But key questions remain about when exactly water first appeared on Mars and how it evolved and disappeared over time. Scientists analyzed a sample from the Black Beauty meteorite, also known as NWA 7034, that was found in the Sahara Desert in 2011. The meteorite was ejected from the Martian surface after another celestial object hit the planet between 5 million and 10 million years ago, and fragments of it have served as a key source of studying ancient Mars for years. The new study, published in the journal Science Advances on November 22nd, focused on a single grain of the mineral zircon spotted within the meteorite. The team's analysis shows that water was present just 100 million years after the planet formed, which suggests that Mars may have been able to support life at some point in its history. Our data suggests the presence of water in the crust of Mars at a comparable time to the earliest evidence for water on Earth's surface, around 4.4 billion years ago, said lead study author Jack Gillespie, researcher at the University of Lausanne's Faculty of Geosciences and Environment in Switzerland, in a statement. This discovery provides new evidence for understanding the planetary evolution of Mars, the processes that took place on it, and its potential to have harbored life. Minerals as time capsules. Rocks may hold the answers to some of the biggest remaining questions about Mars, including how much water was present and whether life ever existed on the planet. That's why meteorites like Black Beauty are of such interest to scientists. Carl Agee, a professor and director of the Institute of Meteoritics at the University of New Mexico, first presented the space rock to the scientific community in 2013. The Black Beauty meteorite contains hundreds of rock and mineral fragments, each with a different part of the 4.5 billion years of Martian history, said study co-author Dr. Aaron Cavesey, a planetary scientist and senior lecturer of the Space Science and Technology Center at Curtin University, in an email. It is the only source of pieces for the geological puzzle of pre-Noachian Mars. The Noachian period occurred from 4.1 to 3.7 billion years ago, and little is known from direct measurements dating to the pre-Noachian period on Mars, between 4.5 billion and 4.1 billion years ago, though it's crucial to understand because it serves as the first page in the Mars history book, Cavesey said. But Black Beauty has revealed some of its secrets. Many of the rock fragments the meteorite contains show that the Martian crust endured a number of impacts, causing a massive amount of upheaval on the planet's surface, he said. The space rock also contains the oldest known pieces of Mars, including the oldest zircons, Cavesey said. Zircon, used in products such as jewelry, ceramic tiles, and medical implants, is a hardy mineral that can help scientists peer into the past and determine the conditions present when it crystallized, including the temperature at the time and whether the mineral interacted with water. Zircon contains traces of uranium, an element that acts as a natural clock, said Gillespie, who was a postdoctoral research associate at Curtin University's School of Earth and Planetary Sciences at the time of the study. This element decays to lead over time at a precisely known rate. By comparing the ratio of uranium to lead, we can calculate the age of crystal formation. The zircon in Black Beauty was unaltered by its trip to Earth and fiery entrance into our planet's atmosphere before crashing down in the Sahara, because it was protected by its location within the meteorite's interior, Cavesey said. During the analysis of the zircon grain, the study team detected unusual amounts of iron, sodium, and aluminum, suggesting that water-rich fluids left these traces on the zircon as it formed 4.45 billion years ago. Such elements aren't usually found in crystalline zircon, but the researchers' atom-scale studies of the zircon showed the elements incorporated into the crystal structure and lined up like fruit stands in a market, Cavesi said. We could tell by the patterns of how the iron, aluminum, and sodium are found inside the zircon that they were incorporated into the grain as it grew, like layers in an onion, Cavesi said. On Earth, zircons from hydrothermal systems, which form when water is heated by subsurface volcanic activity like the upward flow of hot magma, have similar patterns to those found in Black Beauty. If hydrothermal systems existed in the Martian crust 4.45 billion years ago, liquid water likely made its way to the surface. Our experience on Earth shows that water is critical for habitats capable of supporting life, Cavesi said. Many environments on Earth host life in hot water systems, including hot springs and hydrothermal vents. Such environments may have given rise to the earliest life forms on Earth. Our new study shows that the crust of Mars was warm and wet in the pre-Noachian period, meaning that habitable environments may have existed at that time. Getting up close with Mars, Cavesi is curious to determine whether hydrothermal systems like hot springs were prevalent when magma was helping form the red planet's crust between 4.48 billion and 4.43 billion years ago, or if they were more episodic. If hydrothermal systems were a stable feature on early Mars, it would indicate habitable conditions may have persisted over a considerable time span, Cavesi said. This is now a testable hypothesis that can be addressed by collecting more data from Martian zircons. Until samples can be returned directly from Mars, the Black Beauty meteorite is one of the best windows into how the Martian crust formed and what the early surface of Mars was like, said Brian E. Horgan, co-investigator on the Perseverance rover mission and professor of planetary science at Purdue University in West Lafayette, Indiana. Horgan was not involved in this study. Finding evidence of hydrothermal systems within the subsurface from one tiny grain of zircon aligns with scientific theories on the amount of water and volcanic activity that existed on ancient Mars, she said. And these earliest potentially habitable environments would have been shielded from radiation by a strong planetary magnetic field, which Mars lacks today, Horgan added. Scientists are still trying to explain how the red planet lost its protective magnetic field. Currently, the Perseverance rover is climbing the rim of Jezero crater on Mars, an ancient lake once filled with water 3.7 billion years ago. Some of the rocks the rover has encountered may have been formed by hydrothermal systems, Horgan said. The rover will take samples from the rocks because they could preserve evidence of ancient microbial life. As much as the meteorites can tell us, we can do even better with a carefully selected and intact rock sample from a known location on Mars with good geologic context, Horgan said. So this paper is a great motivation for bringing our Mars samples back to Earth to study with the same level of detail for years to come,